Project 3.7, 4517, Gray Code by Atticus Stipulaty. The purpose of this project is to take the outputs from a dial and convert the gray code so that the value being emitted is displayed on a 7-segment display using Carnot mapping. Although briefly reflected on during the grade 10 portion of this course, the fundamental concept found within this project has to deal with gray code. Gray code is a sequence of binary numbers where each successive value differs by only one singular bit from the previous, meaning that only one binary digit changes at a time. As explored previously, binary digits count from left to right, with each digit moving left is equal to 2 to the n, where n is the placement away from 0. However, mentioned previously, since only one bit can change in gray code, it counts as 000, 001, 011, 010, where in binary, this counting would be seen as 0132. The backbone of this project has to deal with something referred to as gate-level minimization, the design task of finding a heavily simplified gate-level implementation of the Boolean functions that describe the digital circuit. However, before we discuss what Carnot mapping is and what its function truly is, it is useful to first examine what a minterm is and how Carnot mapping takes advantage over them. Since a binary variable may appear in two forms, that being standard form x or its complement form x prime, and may appear in either form, in a variable circuit there are four possible combinations: x prime, y, x, y prime, and xy. As a result of such, each of these and terms are referred to as minterms. Each minterm represents exactly one row in a truth table where the output is true and is written as a product of all input variables. As hinted at before, K-mapping is a construction by assembling the minterms in terms of gray code in which only one variable changes by moving from adjacent square to adjacent square, with each square representing one of the possible combinations of inputs. When two adjacent minterms differ by only one variable, the variable can be eliminated using Boolean algebra. As a result of there being a 4-variable K-map, the combination of adjacent squared that is useful during the simplification process is easily determined from inspection of the 4-variable map. One square represents one minterm, giving a term with 4 literals. 2 gives a term of 3 literals. 4, 2 literals. 8, 1 literal. And 16 adjacent squares produce a function that is always equal to 1. Within the confines of this project, instead of setting up the K-map in terms of gray code variables, for simplicity, the least significant bit is represented by A and the most significant bit is D, hence the tables. Since the project is converting the gray code being emitted from a dial, the circuit included takes the input from the dial and splits it off into 7 potential paths, with each controlling one specific segment of the 7-segment display. This is an example of segment of A, where this is the truth table for the K-map. The logic for this truth table was found in the 4 ones in the second and third column and the second and third row that form the argument AC as D prime, D, B prime, and B simplify to 1. Moreover, B prime D was found from within column 1 and 2, row 3 and 4, as the 4 adjacent squares come together, reducing C and A to 1. The rest were found as followed. B, C, D prime is found in row 1, column 3 and 4, with 2 adjacent squares forming 3 literals. AC prime is found in row 2 and 3, column 3 and 4, with 4 adjacent squares forming 2 literals. AB prime is found row 1 through 4, column 1, with 4 adjacent squares forming 2 literals. This is the most simplified expression containing 6 AND gates, 4 OR gates, and 7 NOT gates. Pause the video for the following other segments: B, C, D, E, F, G. The Falstad depictions of each are linked below. However, these tables result in a total chip count of 46 AND gates, 23 OR gates, and 38 NOT gates. However, since each input, that being A, B, C, and D, only have 2 states, that being primed or unprimed, once primed, that value can just be reused throughout the entire circuit, meaning one chip can cover the 4 NOT gates that are needed at the start. Since each chip contains 4 of each gate, this means the total chip count for this project is equivalent to 9 AND chips, 6 OR chips, and 1 NOT chip. Thank you for taking the time to listen to my video on Project 3.7, 4517, Gray Code.